Hi, welcome back. In the last video, we saw two new functions, the impulse and the step, in discrete time. And in this video, we're going to look at those guys, but in continuous time. So we want to know, how can we take what we just learned in the discrete time and find out what its analogous, or the analogous properties are in continuous time. So let's have a look. Okay, so in continuous time, we're going to start with the impulse, and it's a little tricky to define. If you remember from discrete time, we had a 1 at the origin and 0 everywhere else. Okay, this was this delta of n. This was n. Now, if we do something similar in continuous time, we have an issue that we run into. Can you think of what that issue might be? Well, the issue is that we're going to run into problems when we try to define how short in duration the signal is. In discrete time, it was obvious. Well, we're just going to make 1 unit of time be 1. But what's that equivalent in continuous time, right? We don't know exactly. How short are we going to make that pulse? Okay, so what I'm going to do is I'm going to call this pulse delta sub delta, and I'm going to say it's just got a duration like this. So it's 0 until the origin, and then it shoots up to some value, and then it shoots back down, and I'm going to call that time delta right there, delta. Now, one of the important properties in the discrete case was that the delta function summed to 1. And it was this property that led to the two important properties, which were that the impulse has unit energy and the shifting property. So we're going to want something similar in continuous time. We're going to want this continuous time impulse, dt, to integrate to 1. There's no such thing as a summation, right? In continuous time, now we're integrating. So we want this thing to integrate to 1. So that means I need to make this height 1 over delta. Okay, and we know that the integral is the area underneath the curve. So if the height is 1 over delta and the width is delta, then the area of a rectangle, 1 over delta times delta, gives me 1. Okay, so that's the start. So now we have this pulse that has this width delta, and it has an area of 1, which is good. That's what we want. But we're going to idealize this pulse, and we're going to take the limit as delta goes to 0 of this delta sub delta function. Now imagine what that looks like. So as delta becomes 0, this edge, this transition, comes to the origin, but also 1 over delta gets higher and higher and higher and goes to infinity. So the way we represent this is with a spike, like that. And we label that spike with a 1, and the 1 signifies that this thing integrates, the spike integrates to 1. It has unit energy. It integrates to 1 because of how we set it up. We set it up to do that, exactly that, right? Have unit energy, unit area. So now be careful here. I don't want you to draw this with a stem plot. I don't want you to draw it like this, because that suggests that it's discrete. We're working with continuous signals now. So this signal, it seems kind of strange, but it's 0, and then it jumps to infinity. The arrow means it goes to infinity, but it integrates to 1, and then it comes back to 0. And this is what we're calling the impulse, the delta function. Okay, that's our delta function in continuous time. So if you didn't follow that, that's okay. What you need to remember about the delta function is the following. It's non-zero. At t equals 0. It is not 1 at t equals 0. The 1 means it integrates to 1, which is the next point. This thing has unit energy. And integrates to 1. And you should know that it is 0 everywhere but at the origin. Okay, so that's what you need to know about the signal. Now, if I had a constant, let's say the number 2 times the impulse, we would represent that similarly with this signal. Well, 2 times 0 is still 0, so it's 0 everywhere here. But then we have a spike, and it goes to infinity, but the area now is 2, right? It would integrate to 2 because we're scaling it by 2. So that's how we represent that. And then it will follow, you can use the same arguments that we did in the last video, but it follows the sifting. We have the sifting property. Okay, so the sifting property is this. So we're going to integrate from A to B delta of t minus t0 times some function, some signal x of t dt, and this is equal to x of t0 if t0 is contained in that region of integration. And because this is continuous, I'm going to leave off the equal sign as just a formality there, but because it's continuous, it doesn't matter if I really put an equal sign there or not. Not like discrete time matters there. And then it's 0 otherwise. Okay, so I'm not going to prove that, but if you followed what we did in discrete time, it ends up being very similar. So we have the sifting property there that you need to be concerned with. All right, so this impulse, it's kind of weird, right? And it's an idealized signal. All systems have inertia and do not respond instantaneously to system inputs. So, if a pulse of sufficient short duration is applied, the system response will not be affected by the pulse duration, the height, or the shape. Instead, the primary characteristic the system responds to is the net integrated effect of the pulse, meaning the energy. Some systems respond more quickly than others do, but we can always find a pulse that is short enough in duration. So the unit impulse is an idealization, a pulse short enough for any system. And it's going to end up being very important, a very important signal that we're going to use to analyze continuous time systems. Okay. Let's move on to the unit step. Okay, the unit step, we're going to use U again. And it is defined as 1 for t greater than 0 and 0 for t less than 0. So let's observe what that would look like in a plot. Here's t. So we've got 0 for negative time, and then 1 for positive time. here's our signal, and notice it is not defined, or it's undefined, defined at t equals 0. It turns out it's not going to matter because this is continuous. What the value of a signal is at one specific value of time. Okay, so it's not going to matter what it is at t equals 0. Some books have it defined at 1. Some books have it defined as 0. Some books have it defined as 1/2. Your book leaves it undefined at t equals 0, and so we will leave it undefined at t equals 0 as well. So I want you to notice a relationship between the unit step and the unit impulse, and that's this, that the impulse is equal to the derivative of the unit step. Why is that? Well, you know from calculus that the derivative is the slope of the line, right, the tangent line. So here's the unit step. This is u of t. Okay, the slope of this part is 0. I'm going to draw the slope underneath it. So the slope of this part is 0. There's no slope there. And the slope of this part is 0 as well. Then we have an instantaneous jump, but a jump of 1, meaning we have to have something where we accumulate area, like to jump to 1. So here's our instantaneous jump, meaning we go to infinity, but we know that we've accumulated 1 unit of area because the integral, if you go the other way from this to this, then we know we've had to have picked up 1 unit of area there. So this is exactly the impulse. That's my delta. That's not a very good delta, but there it is. Okay, and of course, then you know from calculus that if the derivative of the unit step is equal to the impulse, then the unit step is the integral of the impulse. So and we write this as a running integral like this. This is something that you need to be comfortable with. Okay, let me explain this notation if you're not familiar with it already. This is a running integral. It's the analogous equation to the accumulating function that we saw last video, running integral, the accumulator. Okay, tau here is what's called a dummy variable. When you integrate something and you put in bounds, that something goes away. Like if you were to integrate x from 0 to 1, when you put in the bounds, you're left with a number. You're left with something that does not depend on x. So we want something that we end up with t. We end up with a function of t. And so we don't put t here. We just put some dummy variable, tau or whatever. We could have called this thing whatever we wanted except for t. And it's just a dummy so that when we integrate, the tau goes away and we're left with a function of t. So this is a running integral, meaning you tell me the value of time, and I'm going to accumulate the area, or add the area, right? Integral is area, from minus infinity to that point in time. So let's investigate. If you gave me a time over here, right, whatever that is, I'm going to add all the area up to that point. Well, that's all of that is 0, so I should have a 0 here, and I do. And if I looked at this point, I'm going to add all the area up until this point. Well, that's still all 0, so I should have a 0 here. And now, if you go to the right of the origin, I'm going to add all the area like this up to that point. And how much area have I picked up? 0, 0, 0, 0, and then I pick up area of 1, right? That thing integrates to 1. So right here in time, I should have a 1, and I do. And any value over here contains the impulse when I integrate, and so I'll have 1s over here. So indeed, the unit step is the integral, or the running integral of the impulse. So you need to be aware of that. So in the next video, we're going to run through some examples of how to use the unit step and the impulse, the unit impulse. And we'll look at continuous time and discrete time so we can kind of get a flavor of how these things work, particularly the sifting property of the impulse.